Welcome back to Bite-Sized Breakthroughs, the podcast where we unpack the latest in tech research. Today, we're diving deep into a fascinating paper on automated GUI interaction. I'm your host, Alex Askwell, and with me are Dr. Paige Turner, the lead researcher behind this work, and Professor Wide Spectrum, an expert in the field. Welcome to both of you.
Thanks for having us, Alex. It's a pleasure to be here.
Paige, let's start with the basics. The paper introduces UITARS. What exactly is that?
UITARS is a native GUI agent model designed for automated interaction with graphical user interfaces, or GUIs. Unlike many existing systems, UITARS takes only screenshots as input and performs human-like actions such as keyboard and mouse operations entirely end-to-end. This means it doesn't rely on external text descriptions of the interface, like HTML code, which are often platform-specific and can have issues with generalizability. It's designed to be adaptable and scalable across different environments.
And WID, how does this fit into the broader history of GUI agents?
Well, historically, GUI agents started with rule-based systems. Think of robotic process automation, or RPA. These were good for very structured, repetitive tasks, but they were essentially just following predefined rules. They couldn't learn from their environment, and any change required manual intervention, like rewriting rules or adapting APIs. Then we moved to modular frameworks, often leveraging large language models like GPT-4. These systems use different modules for perception, reasoning, and action, and each module was often handcrafted, which created issues with scalability, maintainability, and efficiency. UITARS, in contrast, represents a move toward a unified end-to-end model that learns directly from data.
So we've moved from inflexible rule-based to modular but complex to now this end-to-end model. Paige, what makes UITARS different from these more recent modular approaches?
The key difference lies in how UITARS is designed and trained. Modular approaches use separate components, often relying on large language or vision models like GPT-4o for understanding and reasoning, with extra modules for grounding, planning, or memory. This modular approach, while allowing for rapid development of specific tools, relies heavily on human input to handcraft rules, prompts, or workflows, limiting its scalability and adaptability. UITARS, on the other hand, uses a unified architecture that learns everything end-to-end. We collect large-scale datasets of images, actions, and thoughts, and feed all of this data into a single model. This eliminates the need for manual engineering and allows the model to learn from data directly. This makes UITARS more robust and generalizable across different scenarios.
That sounds like a significant shift. Could you elaborate on some of the specific innovations in UITARS?
Certainly, we've incorporated several key innovations. First, we have what we call enhanced perception. This involves using a large-scale, curated dataset of GUI screenshots along with metadata about each element on the screen. This data is used for training our model in diverse tasks that enables it to have a better understanding of UI elements and their relationships. This includes tasks such as element description, where the model must provide fine-grained details of each UI component, dense captioning, where the model describes the entire interface layout, state transition captioning, where it identifies subtle changes in the screen, question answering to test reasoning ability about the GUI, and set of mark prompting, where visual markers are used to enhance the understanding of the relationship between elements and the surrounding context.
So not just object detection, but a deeper understanding of what's happening on the screen.
Exactly. Second is unified action modeling. We standardized actions, such as click, type, scroll, into a unified space that is valid across various platforms, mobile, desktop, web, allowing knowledge transfer and reducing complexity. We paired this with a large-scale dataset of action traces, enabling precise grounding of actions to specific GUI elements. For instance, we trained the model to predict the screen coordinates for a click action from a description of a button, such as click on submit.
That makes it platform-agnostic, which is a big plus, I assume. What else did you do?
Third, we incorporated System 2 reasoning. Unlike the fast, intuitive System 1 thinking, System 2 refers to deliberate, analytical thinking. We achieved this by making the model generate explicit thoughts before each action. These thoughts follow reasoning patterns such as task decomposition, where a complex goal is broken down into smaller steps, long-term consistency, ensuring the model stays aligned with the overall goal, milestone recognition to track task progress, trial and error for hypothetical action testing, and reflection for self-correction. We also leverage a large-scale collection of over 6 million GUI tutorials to provide a broad understanding of the various ways a user can interact with an interface. We found that the model's ability to learn to plan and recover from errors significantly improved performance.
So the model doesn't just blindly act, it plans and reflects, almost like a human.
Precisely. And finally, we implemented iterative training with reflective online traces. A significant hurdle for GUI agents is the lack of large-scale, high-quality action traces. We addressed this by using an iterative framework with hundreds of virtual machines where UITARS interacts with various software, websites, etc., and produces action traces. These traces are then filtered based on rules, VLM scoring, and human review to ensure high quality, and these are then used to retrain the model. This allows the model to continuously learn from its own mistakes. We also use direct preference optimization, or DPO, to further enhance the model's ability to recover from errors. DPO is a method where we can explicitly tell the model what a wrong action was and then provide a corrected action to teach the model what it should have done instead.
WID, does this iterative training approach represent a departure from existing methodologies?
Absolutely. Traditional methods rely heavily on pre-collected static datasets, which, as we noted, can have issues with generalizability. UITARS online bootstrapping, with its iterative self-improvement loop, allows the model to continuously adapt and improve based on new experiences. This method aligns with the recent trend of active learning, where the model actively seeks out new knowledge and refines its performance, rather than relying solely on predefined tasks.
So the model is actively learning and adapting, not just passively following directions. Paige, let's dive deeper into the methodology. How exactly did you achieve this end-to-end learning and handle the unique challenges of GUI interaction?
Our methodology is structured around several key aspects. First, we focused on building the large-scale, high-quality datasets needed for training. For perception, we curated a diverse set of GUI screenshots, both by automated scraping and human-driven actions, with metadata such as element type, text content, depth, and bounding boxes for each element. Then, we had annotators create labels based on 5 core tasks: element description, dense captioning, state transition captioning, question answering, and set of mark prompting to ensure a comprehensive representation of various UI interfaces. Our action data came from a combination of our own annotated data and other open-source datasets. These were all standardized into a unified action space with consistent semantics. For the System 2 reasoning component, we leveraged 6 million GUI tutorials that went through multiple stages of filtering to isolate relevant data. Finally, we augmented action traces with reflective thoughts using VLM annotations and our unique thought bootstrapping method that uses candidate generation to select a thought that truly matches the action.
And how did you ensure that the model was able to handle the variable and dynamic nature of GUIs?
That's a very important aspect. We address the dynamic nature of GUIs by requiring the model to continuously perceive and adapt to changes as the interface evolves. Our state transition captioning forces the model to understand what is changing and how the interface transitions in response to actions. The iterative training also allows the model to adapt to evolving interfaces, and the reflection component enables the model to recover from errors or unexpected responses. To handle variability in GUI layout, we use a unified action space that abstracts platform-specific actions into a common set of operations, as well as device-specific actions when appropriate.
Okay, let's talk about that unified action space. How does this work?
The unified action space is a standardized vocabulary of actions that are semantically equivalent across different devices and platforms. This allows the agent to have a consistent method of interacting with different interfaces. It includes general actions like click XY, drag X1, Y1, X2, Y2, scroll X, Y direction, type content, wait, finished, and call user, which are valid across platforms and devices. Then we have device-specific actions such as desktop hotkey key, left double XY, and right single XY for desktop, and mobile long press XY, press back, press home, and press enter for mobile.
This sounds like it makes scaling the model easier, right?
Precisely. By standardizing actions and making them semantically consistent, we can more easily transfer knowledge across different platforms without needing separate modules or coding logic. This allows the model to learn generalizable skills that aren't tied to specific devices.
Paige, you mentioned thought bootstrapping. Can you go a little more into this idea, as it sounds like a really novel approach?
Yes, thought bootstrapping is a unique method we developed to generate high-quality thoughts for our System 2 reasoning component. Normally, we would just annotate the thoughts given the action, but that can lead to false positives, where the thoughts appear to align with the action, but they don't accurately reflect the reasoning process that should have led to it. To address this, we use our early-stage UITARS model to generate multiple potential thought-action pairs given an observation sequence. We then select the thought-action pair that corresponds to the correct or ground truth action in the trace. This helps to create a causal link between the reasoning and the final action, resulting in higher quality annotations.
Okay, so instead of just describing what happened after the fact, you're effectively getting the model to show its thought process in advance. Wed, what do you make of this thought bootstrapping method?
It's a very clever approach. It addresses a common issue in agent training, where you need to guide the agent towards the right actions while also encouraging genuine reasoning. The thought bootstrapping approach helps to ensure that the thoughts actually reflect a true decision-making process, rather than just a retrospective justification for an action.
Paige, let's talk about the experimental results now. Where did UITARS really shine?
UITARS demonstrated state-of-the-art performance on more than 10 GUI agent benchmarks. In perception, UITARS 72B scored 82.8 on Visual Web Bench, a significant improvement over GPT-4o, which scored 78.5. We also saw improvements in both WebSarc and ScreenQA Short, showing a high level of understanding in both web and mobile environments. In grounding tasks, we had great results, with UITARS 72B achieving 38.1 on ScreenSpot Pro, and leading scores on ScreenSpot and ScreenSpot V2 as well. On offline agent tasks, we tested multimodal Mind2Web, Android Control, and GUI Odyssey, and UITARS 72B achieved SOTA performance in all metrics. But most notably, the performance gains were the largest on online agent tasks, specifically on the OS World benchmark, which has complex, multi-step operations on real desktop environments. Here, UITARS 72B.DPO achieved scores of 24.6 with 50 steps and 22.7 with 15 steps, outperforming Claude's 22.0 and 14.9 respectively. And on Android World, we achieved a score of 46.6, surpassing GPT-4o's 34.5. This shows how well the model performs in complex and dynamic tasks.
Those are some impressive numbers. Wid, what do you think these results mean for the field?
These results are very significant, Alex. They demonstrate that end-to-end native models, like UITARS, are not just a theoretical improvement, but are practically superior to existing modular frameworks and other text-based models. The fact that UITARS performed so strongly in complex scenarios like OS World, where models must interact with real software, indicates that we're moving toward GUI agents that can handle real-world tasks effectively. The performance on Android World is also promising because that represents an entirely different interface from OS World. These are difficult problems, so achieving this level of performance on them is a major step forward.
Paige, you mentioned the direct preference optimization, or DPO technique. How exactly did that contribute to the model's performance, especially in OS World?
DPO was a critical component of our approach, especially for OS World. While traditional supervised fine-tuning, SFT, trains the model on a good path, it does not explicitly consider what not to do. DPO addresses this by using both corrected and erroneous actions generated during online bootstrapping. We train the model to learn a preference for the corrected actions and penalize the erroneous ones by directly optimizing the DPO loss. We found that this method greatly improved the model's ability to recognize and recover from errors, which leads to significant performance increases, especially for complex online tasks like OS World. For instance, in our experiments, we saw the model's scores on OS World increase by approximately 30% after DPO training.
So you're not just showing the model the correct path, but also showing it what not to do. That makes a lot of sense. You also conducted an ablation study on System 1 and System 2 reasoning. What did you find?
Yes, we wanted to compare the effects of intuitive, System 1, and deliberate, System 2, reasoning. We found that in controlled in-domain environments, System 2 initially performed slightly worse than System 1 when using a single sampled output because it would make errors in the intermediate steps of the reasoning process. However, with increased numbers of sampled output candidates, 16 or 64, System 2 showed a clear advantage. The increased diversity in the decision space allows it to overcome flawed reasoning paths. This shows that System 2 reasoning needs multiple samples to explore diverse actions and paths to make optimal decisions. What was most interesting was that in our out-of-domain setting, Android World, System 2 outperformed System 1 even with a single sample output, indicating that it has a superior ability to generalize to unseen scenarios. This demonstrates that the additional reasoning capabilities become increasingly important as we move to less familiar environments.
That's a significant finding, that System 2 reasoning is actually more useful in complex out-of-domain scenarios. What do you make of that?
It highlights an important point about generalization in AI systems. System 1 reasoning, or fast heuristic thinking, can work well in familiar tasks, but it struggles when it encounters new or unexpected problems. System 2 reasoning, with its detailed planning and reflection process, provides the necessary mechanisms to adapt to these novel situations. It aligns with recent findings in cognitive science as well, where similar two-system models of cognition are proposed. The findings from UITARS experiments suggest that deliberate reasoning is key to building robust and adaptable autonomous agents.
Paige, what are some limitations of UITARS and where do you see the need for further research?
While UITARS represents a significant step forward, it still has some limitations that we need to address. First, the model's memory is limited by the sequence length and the number of previous observations. This means it might struggle with very long tasks. Additionally, although UITARS shows significant generalization, it could still encounter issues in completely novel, unseen environments, which we want to test going forward. The online bootstrapping process, while effective, still relies on human review, and we need to improve that to achieve complete autonomy. Finally, we used virtual machines for our experiments, and real-world scenarios could introduce unexpected variability that the model would have to adapt to.
And how do you plan to tackle those challenges? What's next for UITARS?
We plan to focus on several areas for future research. First, we want to explore active and lifelong learning strategies, enabling the agent to autonomously drive its own learning, reducing the need for human intervention. We also need to expand the context window of the model to improve its memory and ability to handle longer tasks. As mentioned, exploring methods to further reduce human review in our iterative training loop is another priority. And finally, we need to further explore differences between the model's behavior in offline and online tasks to improve our evaluation metrics to reflect real-world performance. This will probably require us to develop more robust methods for data augmentation and synthesis.
What are the broader implications of this work, and what other applications can you see?
The broader impact is substantial. This research moves us closer to a world with truly autonomous agents that can interact seamlessly with digital interfaces. We're not just talking about basic automation. We're talking about intelligent assistants that can perform complex tasks across a variety of platforms and applications. This technology can revolutionize software testing, improve accessibility for users with disabilities, streamline workflows for a range of industries, and ultimately change how we interact with computers. Imagine a future where you don't need to learn complex interfaces or spend time on repetitive tasks. You can just tell the computer what to do, and it can execute everything on the screen for you. The potential here is transformative.
That's incredibly exciting and also a bit daunting. What specific use cases do you both envision for UITARS or similar systems?
Well, think of automated software testing. Instead of relying on humans to click through interfaces for every possible scenario, UITARS could do it automatically. We could also see significant improvements to assistive technologies for disabled users, providing alternative ways to interact with software. In various industries from creative to scientific, many tasks can be automated through GUI control. Finally, we could also see improved virtual assistants that can handle far more complex tasks through screen interaction.
Indeed, the ability to have an agent interact with any software or website just like a human opens a plethora of use cases, as Paige mentioned. Think of robotic process automation, or RPA, that is not limited by APIs or underlying system permissions. It can simply watch what the user is doing and execute tasks. That level of generality is simply not available using current state-of-the-art techniques, and that is what sets this apart.
This has been a truly enlightening discussion. Before we wrap up, what are the key takeaways, Paige?
In summary, UITARS represents a significant step towards truly autonomous GUI agents. By using an end-to-end architecture, enhanced perception, unified action modeling, System 2 reasoning, and iterative training with reflective online traces, we've shown that it's possible to build models that outperform existing methods and move towards a world where computers can interact with graphical user interfaces just like humans. The main innovation comes from the shift from manually designed modular frameworks to a fully data-driven end-to-end model, capable of generalizing across different platforms and tasks. The findings have strong implications for fields like automation, accessibility, and general AI development.
And to reinforce those points, the work introduces a new method for GUI interaction, going beyond the limitations of traditional textual representations and handcrafted agent frameworks. It shows that by leveraging large-scale datasets, end-to-end learning, and reflective training, we can create GUI agents with a level of adaptability and generalizability that was previously not available.
Thank you both for sharing your expertise and insights. That was a fascinating look into the future of GUI interaction, and thank you listeners for joining us on Bite-Sized Breakthroughs. Until next time.